Still talking about universal law of gravitation. I've got this little prince, or whoever this is, sitting on a planet. And if you know your French literature, then maybe you know who the little prince is. If you don't, it doesn't really matter, okay? We just have this person standing on a planet. We're going to pretend that this is planet Earth. And so obviously the person is drawn not to scale. Just keep in mind that when we're talking about a person on a planet, when it is to scale, notice that the distance between the ground and their center of mass, their belly button, if you like, is going to be negligible, right? Like, this is obviously a non-scale diagram of a person on a planet. So think about the fact that we don't have to add on the person's height when they're sitting on a planet. We're just going to call it P for person, and we'll call it E for Earth. When we're talking about these universal law of gravitation problems, we often talk about when you're sitting on the surface of a planet, we talk about the distance between the center of mass of the person and the center of mass of Earth as being just the radius of Earth itself. So 6.38 times 10 to the power of 6 meters. Can somebody look up for me? What's the mass of Earth? Oh, no, look it up. It's actually on your equation sheet too. What's the mass of our planet? Yeah?
No, I have a question. What is that symbol?
Where?
Under the R.
Oh, this is the letter E, capital E.
E.
Radius of the Earth. What's the mass of Earth? Got to be able to find it. Anybody got it? Yeah. So we got 5.97 times 10 to the power of 24 kilograms. The mass of our planet. No? We're going to make an assumption. We're going to say, just choose a nice round number. We're going to say that the mass of this prince, this person, is 100 kilograms. Nice round number. Okay? And maybe we should put it in writing. The distance from the center of mass of Earth center of mass of Earth, and we could write in just above center of mass C of M, center of mass of Earth to the person is very large. Compared to the person's height. Therefore, in a situation like this, disregard the human's height. But maybe there's an actual question we have to solve. Find the force of gravitational attraction between the person and Earth. Find the force of attraction between the person and Earth. And if that's all we were trying to do, we'd just say, well, okay, well, Fg, which really is gravitational force, and you could think of it as force of 2 acting on 1 or force of 1 acting on 2. Or in this case, even more specifically, we wouldn't use 1 and 2 as our indices. We talk about this as the force of Earth acting on the person. You could use even like appropriate letters for it. We would say that's equal to G times the mass of the Earth times the mass of the person divided by the radius squared. And in this case, the radius, the distance between their centers of mass based on this little statement here, is basically RE, because we say that the height of the person is negligible. And if we sub in our values, we say, okay, well, that's 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared times the mass of the Earth, 5.97 times 10 to the 24 kilograms, times the mass of the person, 100 kilograms, divided by the distance between their centers of mass, so 6.38 times 10 to the power of 6. Now the thing is, when you type all this into your calculator, you got to remember that you're going to be squaring this thing. So for a lot of us, maybe you want to use all the brackets that you need. And especially in the denominator, what I found is that if I coach people to do an open bracket, and then another open bracket, and then the 6.38 times 10 to the power of 6. Oh, I forgot to put the meters in there. And then close bracket, and then square that, and then close bracket again. It seems to go better into their calculator, okay? So I think data entry is one of the biggest hurdles for this particular question, is just trying to get all this scientific notation in there and have the syntax be right. So what I want people to do right now, take a minute. Could you please type this all into your calculator? I'll tell you right now, the answer should start with a 9. Okay, so the answer is going to start with a 9. Type it all into your calculator. Make sure you can actually do it. I don't want you to just write down the answer. I want to make sure that you can use your tool to get to this. Yeah?
Units after like you get the answer I forgot.
Well, the units for force is newtons.
So would the answer just be newtons?
Yeah, in newtons, yeah. Yeah, and you can go through and you can kind of prove to yourself that all the units are going to cancel out except for newtons, but they definitely will. Now, depending on your calculator, when you do your scientific notation, because it seems like this is a hurdle for some people, you might do your scientific notation as 10, and then there may be a y to the x button, and then 24. That might be the button sequence that you're going to use. You may have a button that looks like 10, and then up arrow 24. If you have some other buttons on your calculator, that's fine. But those are two common ones, okay? All right, I want to hear from the room. What do people get for their force value? Rhea? 0.27? Oh, one. Nice. All right. Newtons. That's fantastic. So we got this force due to gravity of about 978 newtons. Looks like we have 3 sig figs here, sure. That's brilliant. Now, the thing is that we know that this is the force of the Earth acting on the person gravitationally, and we also, I think we should know at this point that the person is acting on the Earth with this exact same force. But because the Earth is really, really big, the acceleration of the Earth is like basically 0, right? But it really is a mutual attractive force. The person standing on the planet is attracted to the Earth, and the Earth is attracted to the person. But because the person's mass is really, really small, they notice that acceleration as they fall. Okay? I want to think about these two other folks down here, and depending on your childhood cartoon diet when you were a kid, does anybody recognize these two? Few people? Anybody know their names? I heard it. Phineas and Ferb. And if you don't know any, then it's not Phineas and Ferb. It's Phineas and what's the girl's name? Isabella. Isabella's got a crush on Phineas, but he's oblivious because he's too into the science, I think, or whatever. I don't know. Anyway, what Phineas doesn't realize yet, I think in the series finale, he dates Isabella because I don't know. They needed to resolve the loose end or something, so you should follow up on that yourself, I guess. Thank you, Disney. So that's weird. But let's just say that these two, even before the series finale, they were attracted to each other. But gravitationally speaking. And if you come up to somebody at a physics party and you say, you could be a nice young person, you could say, hey, to the special someone, did you know that you're attracted to me? And they may well say, yes, I am. But just in case they give you some dubious answer, you can say, yes, scientifically speaking. And you can pull out the calculations. So let me show you how to do the math, okay? Just in case this takes you to the next level. So nice round numbers. Isabella has a mass of 200 kilograms. She's obviously taller than Phineas. Phineas is smaller, 100 kilograms. These may or may not be, I don't know the density of cartoon characters, okay? 100 kilograms. And as these two are standing next to each other, let's just say that they stand a distance, because you want to make sure that you leave the cartoon world fairly respectable. Let's say that they're just 3 meters apart from each other while they're talking. That's a pretty good distance, even at a physics party. And if she wanted to explain to him exactly how attracted to her he is, one thing we could notice is that force of 1 acting on 2 is going to be equal but opposite to force of 2 acting on 1. So not only is he attracted to her, but this argument proves that she's attracted to him. Okay? Now the magnitudes are going to be equal to each other. That's Newton's third law. So we could say that attractive force, Fg, is going to be g times mass 1 times mass 2 over r squared. We sub in our values, 6.67 times 10 to the power of negative 11, Newton meter squared divided by kilograms squared, multiplied by 200 kilograms, multiplied by 100 kilograms, divided by 3 meters. Don't forget to square it. And here they are at a lovely physics party. How attracted are they to each other? Help me out with this one. This is another data entry thing. So if you're watching on video, actually pull out a calculator. Make sure you can do it. If you're alive, make sure you can do it. Answer starts with a 1. You feel confident? You got it? Nope. Starts with a 1.
I feel very confident.
What do you got?
1.630, and then a lot of 4s.
No.
No?
Yes. Yes. Sorry, guys. And so that's why we're doing this practice of doing data entry. You're going to misenter the data sometimes. Make sure you can get it.
Oh, it's squared.
Yeah, don't forget to square the 3. Most common mistake with data entry on this one. Times 10 to the, you say negative 7? Yep, negative 7. And the units are newtons. And if we're going to 3 sig figs here, 1.48 times 10 to the negative 7 newtons. That's how attracted. Now, he could come back to her and he could say, Isabella, we are attracted to each other. A lot or a little, though? A little. It's a children's show, right? 10 to the power of negative 7 newtons. Order of magnitude. By the end of the series, they've matured. Fine, whatever. I think they go off to college or something. Anyway, 10 to the power of negative 7 newtons. Now, people say, well, which one is the one that stays put? Which is the one that is stationary? You know, like when things get attracted to each other gravitationally, they're actually attracted to a center of mass of the system. They're actually attracted to a point somewhere around there. It's not like he's attracted to her and she's attracted to him. They're attracted to a central point. Now, in this case, this is not a symmetrical system. Which side is it, I guess, unbalanced towards? Yeah, Isabella. And in fact, look, she's 2, he's, okay, so they're actually attracted to a point somewhere around there. And so she could say, yes, you are attracted to me a little bit, but we're both attracted to the same point. Maybe we should get together sometime, something like that. And like on this, you know, I'm not suggesting that this could be like anything that starts anything in your romantic life, but I do want to point this out. if you're at a party with a lot of people, not just two people, physics parties usually have a lot of people at them, right? Very popular physics people. And you can imagine that this particle and this particle are attracted to each other, agreed? Sorry, party goer. But also this one and this one are also attracted to each other. Physics parties are pretty crazy places, right? And then this one and this one are attracted to each other. And as I think about it, this one and this one are attracted to each other. And I go through this, can you imagine that you could be at the physics party and Phineas could shout out to the whole room, "Hey gang, we're all attracted to each other." This is really get things going, you know? Like what a great way to start friendships. But interestingly, it doesn't have to stay at the physics party. This could be a cosmogony thing. Can you imagine these are not people at a physics party? These are pieces of rock in interstellar space. What happens if I let them sit there for thousands, millions of years? What are they going to do? Yeah?
Come together.
Yeah, they'll come together. They'll coalesce, right? And so people look up at the skies. They get the telescopes and they see not just chunks of rock, but dust. Over periods of time, can you imagine that a nebula, which is basically a big dust cloud, could experience just exactly this? And eventually, all these little dust particles would coalesce because they're just partiers at the physics party. They're all attracted to each other. And under enough attractive force, if there's enough stuff there, there would be enough attractive force to cause a new star to ignite. That's cool, right? So, I mean, it goes from young love to making stars form. And that could be a whole chemistry party thing where you say, do you know that we're all really made of stars? And we can get into the periodic table and all that sort of stuff, how like stellar fusion makes everything around us. Like, oh my gosh, wow. Like, I'm telling you, science is a great way to meet people. Okay, anyway, so next column over, I want to think about this. Don't ask my wife if I said that to her at a physics party at some point. I didn't say that. I actually had a statistical argument. Anyway, and yet she married me. All right, so I've got this satellite that's in orbit around the Earth, okay? And we already established up above with that prince that there's a radius to the Earth. When satellites go around the Earth, we also talk about there being an orbital radius. And when satellites are above the Earth, there are even people that talk about the altitude. And I want to make sure it's really clear that these are all very different things. When we talked about a prince standing on a planet, notice that the height of the prince we claimed is negligible compared to the radius of the planet. But when we scale things up to satellites, the altitude is not negligible anymore, right? We're talking about not just a prince. It's a satellite. It's way out there. It's far from the center of mass is far from the surface of the planet. And so I want to say that, hey, the orbital radius, I'll just call it our orbit, is going to be equal to RE plus the altitude. I'll just call it alt, just for short. Put it as a binomial. And I was asking a student one time, what would be a reasonable mass for a satellite? I had the student that was really into space stuff. He said, oh, about 1,000 kilograms isn't a terrible mass for a large satellite, telecommunication satellite maybe. And of course, I know that these masses can change as technology changes. But we're going to say that the mass of the Earth is about 5.97 times 10 to the power of 24 kilograms. We looked that up already. We've got an altitude. I'm going to introduce this as new information. The altitude is going to be, let's make it be 2.00 times 10 to the power of 7 meters. So if you're somebody who's into numbers, the altitude is 20 million meters. That's a lot of meters, okay? So definitely not nothing. And then the radius of the Earth is smaller than that. What do we say? 6.38 times 10 to the power of 6 meters. And so as this satellite orbits around the Earth, the thing that's binding it to the Earth is the force due to gravity, right? So we're scaling this up to something more than just, dating scenarios. Like this is something that we care about for telecommunications. We say, okay, well, We'll make a question. What force is keeping the satellite in orbit? And obviously it's gravity, but I mean, like, what value is that gravitational force? And we might later on talk about F big G being the centripetal, what gives rise to the centripetal force in this situation, and we could talk about centripetal force and centripetal acceleration, all that sort of thing. But right now I just want to say, like, what force, right? What is the value? Okay, so F big G is equal to G m1 m2 over r squared. Specifically in this case, because I've got like two different r values and an altitude, we're going to have to talk about what the r value is. So maybe I'll just put it over here. My values, I've got 6, because this would be r orbit, right? This isn't re. 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared times mass 1, which is the Earth. We'll let Earth be mass 1. 5.97 times 10 to the 24 kilograms times 1,000 kilograms divided by, and again, I'm going to ask you guys to do the data entry just to make sure that you really can do it. But in the denominator, we're going to make it one level harder than what we've done before, because our orbit isn't just one of these r values, it's that binomial re plus altitude. So re was 6.38 times 10 to the power of 6 meters, and the altitude was 2.00 times 10 to the power of 7 meters. And then the thing that so many people forget, so I'll put it in red, square it. Make sure you square that denominator. A lot of people are going to forget that keystroke if I don't draw your attention to it. Again, if you have a hard time getting that denominator to go properly into your calculator, force extra brackets in there to make sure that your calculator knows that whole thing is in the denominator, okay? Because your calculator is not as smart as you like. I'll tell you right now, the answer should start with a 5. Just to give that confidence. If you got an answer that starts with a 5, shoot your hand up in the air. Let's see what we get. Again, if you're watching video online, actually pull out your calculator and do it. Anybody brave enough to say? Rhea, you got it? First time. You got it the first time. Say it one more time. 572.2035 newtons. Beautiful. Beautiful. Anybody else get the same value? Nice. All right. So bragging rights. We can round this off to significant figures. It looks like we've got 3. So approximately 572 newtons. That's how much force is holding this satellite in orbit. That's the centripetal force that's really keeping the orbit going.